Okay, so we are in week 6, and there's a lot of rules and theorems that you're learning this week dealing with polynomials. And so one of them is the rational zero theorem, which several people do have issues with understanding. And it looks like you're reconnecting, so I will wait. Okay, looks like you're back. Get my mouse to... There we go. Okay, so just to recap some of the terminology we're going to be using, first off, polynomials, because this is something that applies to polynomials. So what is a polynomial? And a polynomial is a function that has a form where your exponents are basically going from high to low. All of your exponents are whole numbers. All of your coefficients are real numbers. That's what makes it a polynomial. And the term with the highest exponent on x is called the leading term. We call the number in front the leading coefficient, and then that highest exponent is called the degree. So I'm going to be using this terminology. Now, the rational zero theorem, it has the word zero in there, so you need to know, well, what exactly are zeros? So if you have a polynomial, any value where you set your polynomial equal to 0 and solve for x, those x values are called zeros. They are where your function is equal to 0 or the y is equal to 0. So every x-intercept is a 0 of a polynomial. And you may have zeros that are complex numbers, so they're not actually, you can't graph them, so they're not x-intercepts. So sometimes you have more zeros than x-intercepts. And a lot of people get confused. Y-intercepts are not zeros, though I've seen people think they are. They are not. It's only places where y is equal to 0 where you can solve for x. So the rational zero theorem is a rule that we can use to try to find zeros of a polynomial. So you have some polynomial, following our rules for polynomials. So P is a factor of the constant term. So you've got a polynomial, the number without the variable, the constant term. P is basically all the factors of that term. So you find that number and then you write down all the numbers that divide evenly into it. That's what a factor is. And then Q, we do the same thing for the leading coefficient. So the first number, you write down all the numbers that divide into it evenly. Those are the factors, and those are all considered Q. And then your possible rational zeros. So rational means they can be written as a fraction, so P over Q. Those are possible rational zeros. You're going to write every combination of P over Q. You're going to have a list of P's, a list of Q's, and then every single possible combination of those written as a fraction gives you your possible rational zeros. Now, the rational zero theorem does not guarantee there are rational zeros. It just says if there is one, it's in this form, and it will be on this list. That's all. So sometimes you have a list of possibilities and none of them are zeros, and that's fine. It's just giving you some numbers to check so that you're not just like picking random numbers to try to find for zeros. So this makes much more sense when we actually see it worked out. So just as a heads up, we have a big storm that just started, so hopefully I don't lose power. I haven't recently, but just in case I disappear, that would be why. So our first example here, we want to list all the possible zeros of f of x equals 8x to the 4th minus 26x cubed minus 27x squared plus 11x plus 4. And actually, I should say all the possible rational zeros, because there may be other zeros as well. So the last number, the factors of 4 give us p. So p are the factors of 4. So those are all the numbers that divide evenly into 4. So that's 1, 2, and 4. The leading coefficient here is 8, and that is what we call Q, the numbers that divide evenly into 8. So factors of 8, so all the numbers that divide into 8 are 1, 2, 4, and 8. So these are all the list of all the possible Q's, and then the list of all the possible P's. And the possible rational zeros are in the form P over Q. And it could be a positive or a negative. So that's one thing. It doesn't specify on our theorem here, but we could have a positive P over Q or a negative version of P over Q. So just keep that in mind. So what I do is I basically make a table. And so in the upper left corner, I put my label P over Q, and I put a plus or minus to remind myself that the number could be positive or negative. And then I write all my P's on top. And I want to make sure that I have gaps. And then I put my Q's. Oops. I wrote Q instead of the actual number. Those are going to be the rows. And I should have started this up a little higher. And then I'm going to fill in this table with P over Q. So I just basically read my P's are going across, Q's are going down. So that's going to be 1 over 1, and then 2 over 1, and 4 over 1. So I'm just taking each value for P and writing it over my first value for Q. And then I'm going to do the same thing in the next row, where now Q is 2. So it's just P over Q. I'm just taking the top number, the column number, divided by the row number. And then I just keep moving down. This helps me keep track so I haven't forgotten any possibilities. I really should have left myself more room here. So I've written them all down, but we need to reduce these because we've got fractions. You always want to reduce your fractions whenever possible. So after I write them down, then I go back and reduce. So 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4. I've got 1/2, 2 over 1, that is 1 again. 4 over 2, that's 2. So these are kind of repeating. So if they're repeating, I just kind of cross it out because I don't need to list it more than once. I've got 1 over 4, 2 over 4 reduces to 1/2, so that's a repeat already on the list. So I'm just going to cross out that box. 4 over 4 reduces to 1, that's already written down. Then I've got 1/8, 2 over 8 reduces to 1/4, so that's already written down. 4 over 8 is the same as 1/2, so that's already written down. So the numbers that I have not crossed out, those are the possible rational zeros. And so that's when it says list all the possible rational zeros, that's what these are. So possible rational zeros. We've got plus or minus 1, so we can have a positive 1 or a negative 1. Plus or minus 2, plus or minus 4, plus or minus 1/2, plus or minus 1/4, and plus or minus 1/8. So these are not guaranteed to be zeros. For this polynomial, the degree is 4, so we have 4 zeros. So of course, we've got more possibilities here than zeros, but it gives you a starting point to start checking to see if these numbers are zeros. And normally we'll check the whole number values first before we check the fractions, just because those are easier. Are there any questions so far? Okay. So I've got another one here. We've got g of x. So we've got x cubed minus 5x squared plus 2x minus 9. So p are factors of 9. It has a minus 9, but we can just ignore the sign because when we write our p over q, we get a positive or a negative version. So you can just ignore the sign. So all the numbers that divide into 9 are 1, 3, and 9. So those are p. Q is what's in front of the leading term. It's a leading coefficient, which if you don't have a number there, it's a 1. So since we started with an x cubed, there's no number, it's just 1. And the only number that divides into 1 is 1. So I'm going to set up my chart, and I'm going to put P, going across, 1, 3, and 9. And then there's only one value for Q, so that makes it nice and easy. And this is actually a pretty simple example because P over Q, Q is just 1, so we're just writing all of these over 1. So we get plus or minus 1, plus or minus 3, and plus or minus 9. Okay, these are the possible rational zeros. So possible rational zeros. So if you don't want to use plus or minus 1, you can write them separately. So 1, negative 1, 3, negative 3, 9, and negative 9. Those are the possible zeros for this, this polynomial. And just so you have something visually so you can kind of think about this, I'm just going to bring up Desmos here. And I'm going to put in our function. G of x equals x cubed minus 5x squared plus 2x minus 9. Okay. So we've got only one rational zero, or 1 0 here, and it's at this value 4.9620. So it looks like a decimal, and you think, okay, I can write that as a fraction, but that's not one of our numbers on our list. This tells us this is actually an irrational zero that was rounded on our example here. So Desmos rounded the value, but this would normally be some sort of square root. I don't know what square root it is. I'd have to go and try to solve this by hand. But if it's not one of these, we found these possible rational zeros, if none of those are zeros, then there are no rational zeros at all, and they're either complex zeros or irrational. So they're going to have a square root in them. And so in this case, this has to be an irrational zero because it's not on our list. We go back to our first example here and graph this one. We had f of x equals 8x to the 4th minus 26x cubed minus 27x squared plus 11x plus 4. So on this, we can see we've got 4 zeros. So if I click on here, we've got 4 spots. And these are all rational zeros. You can see they were all on our list. We had -1, so that's on our list of possible rational zeros. This is -1/4, that's on the list. 1/2, and 4. So in this situation, there are 4 zeros because the degree is 4, and all of them are rational zeros. They all come from this list. Well, compared to the other one, where it was degree 3, which means there's 3 zeros, but 2 of them are complex and 1 is irrational because it's not on the list that we got. So the rational zero theorem doesn't find all of the zeros, it just helps you find the ones that are rational. It doesn't help you find ones, in this case, that were complex numbers or irrational numbers. Are there any questions so far? Okay, we've got another one here, and again, I was just copying and pasting my directions, so for each of these I missed the word rational zeros. So we have n of x equals -16x to the 4th minus 7x cubed plus 2x plus 6. So p comes from our constant. So all the numbers that divide into 6 are 1, 2, 3, and 6. Q comes from our leading coefficient here, and we could ignore the fact that it's negative and just look at the fact that it's 16. So we get 1, 2, 4, 8, and 16. Those are all the numbers that divide evenly into 16. So our possible zeros, or possible rational zeros, I'm going to have P going across, and then Q going down. Hopefully I left myself enough room this time. There we go. So I'm just making sure I've got my chart. P is going across, Q is going down. And then sometimes what I'll do, instead of actually writing the fractions and then reducing it, I'll kind of do it in my head. So 1 over 1 is 1. 2 over 1 is 2. 3 over 1 is 3. 6 over 1 is 6. So those are all pretty easy. Then we've got 1 over 2, so that's 1/2. 2 over 2, which is 1. So sometimes what I do is I don't even write it down. I just, I kind of simplify it as I go and say, okay, I already got that one written down. 3 over 2 is a new one. And then 6 over 2 is 3, so that doesn't need to get written down. Then I have 1 over 4. And you may notice all of them in the first row and all of them in the first column are new and haven't been written, so you can just immediately kind of copy those down. without thinking about it. And then the rest of them may have repeats. So then you have to kind of think about it. So I'm going to start at row 4. 2 over 4 is the same as 1/2. So I've already gotten that written down. Next one's 3 over 4. I don't have that written down. And then 6 over 4 reduces to 3 over 2. So that's written down. Then we've got 2 over 8, which is 1 over 4. That's written down. 3 over 8, that's a new one. 6 over 8 is 3 over 4, that's written down. And then 2 over 16 is 1 over 8. 3 over 16 is new. And then 6 over 16 is 3 over 8, so that's already written down. So there's a lot of possibilities here because you've got the plus or the minus, but these are all the numbers that that are potential zeros for this polynomial. So possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, plus or minus 3/2, plus or minus 1/4, plus or minus 3/4, plus or minus 1/8, plus or minus 3/8, plus or minus 1 over 16, and then the last one is plus or minus 3 over 16. We have a lot of choices, but it's better to have some number of choices rather than to have like an infinite number of numbers that you could try and see if they're zeros. So if I graph this one just to kind of visualize it, so x to the 4th means that we've got 4 zeros. We don't know how many are actually rational. So n x equals negative 16 x to the 4th minus 7x cubed plus 2x plus 6. So it looks like we've got 2 zeros, and notice that these are awkward decimals. They're not on our list. So these, again, these are going to be irrational zeros. Even though they look like they're rounded, they're actually irrational. They've likely got square roots in them. And so there are, according to our picture, I'm going to zoom out to make sure. Yeah, nothing really going on there. So according to our picture, there are actually 0 rational zeros. So if you were trying to find zeros, what would happen is you would go through this list and try to check every single one of these numbers. And then once none of them work, you would decide, oh, there are no rational zeros at all. They need to be complex or irrational. And in complex, always come in pairs. So we have 2 irrational zeros here, which means the other 2 are complex, and those come in pairs, so they have to be 2. And then that adds up to a total number of zeros of 4. So the rational zero theorem is just a starting point to help you figure out what these numbers are, but it doesn't tell you, and it won't give you all of them. It's just numbers to check. Are there any questions so far? Okay, so I'm going to move on to actually using the rational zero theorem to try to find zeros, because that's why it's there. So as I said, it allows us to narrow down our choices, because right now we have technology that finds zeros, but how does the computer do that? How does it know where those zeros are? It uses theorems like this. So what you're learning is what's going on in the background on your calculator and on the background on any websites or any technology that you're using. So you're kind of learning on what the computer's doing here. And so to find zeros using the rational zero theorem, you first use the theorem to just list all of your possibilities. And then you use synthetic division and the remainder theorem to check to see if each possibility is a zero. So if you haven't gone into synthetic division yet, this is how I set it up. So the book sets it up much differently than I do. So the book, oops. If I can get my pen to actually write. Okay, so the book will set up some synthetic division where they have like a number here, and then they have a number, and then they'll put like a number underneath it, and then a line like that. I don't set mine up like that. I set it up like a table. And I do this because when you're checking lots of values, it makes it a lot easier. I don't have to rewrite things as much. So I set it up where I've got my coefficients of the polynomial going across. And then I've got basically one row, and that's the value that I'm checking to see if it's a zero. So that would be, you would pick one of your rational zero numbers. And then that first column always drops down. And then you multiply those together and put the answer up in the next spot. Add going down, and that gives you a new number. Then you multiply, put the answer up here, add going down, gives you a new number. So I follow that pattern. And then this final answer will tell us if it's a zero or not. So if you get a zero in this final box, you have found a zero. If you get something other than zero, you have not. And sometimes I can tell it's not going to become zero, and I just give up and stop. I don't finish it because it's not worth it. So here's an example of, you can find if something's a zero by plugging the number into the actual function, which I have here on the left. And you have to then find your exponents, multiply, add things together, or if you use synthetic division, it's actually faster. You're dealing with smaller numbers, and it's a lot easier. So just a comparison there of why we use synthetic division versus actually plugging in a number and seeing if it's a function value. So I'm going to demonstrate this whole process here. So this says find all the rational zeros. It does not specify find the possible. So no, it doesn't say possible. So what this means is that first we need to find the possible zeros, and then we use synthetic division to see which ones are zeros. So we're going to do what we did with the rational zero theorem and then go a step further. So for P, it's 10. So all the numbers that divide evenly into 10 are 1, 2, 5, and 10. Q here is just a 1. And what makes that really easy is when you have Q as being a 1, your P over Q are just all going to be the whole numbers because they're just all divided by 1. So we've got plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. So those are the possible rational zeros. Now this polynomial has a degree 4 because that's the highest exponent. So that means we have 4 zeros. So if we have found 4 rational zeros, then we can stop because there's not going to be more than 4. That's the maximum number of zeros. So what I'm going to do is set up my synthetic division. I'm going to take the coefficients of our polynomial. 1, I have another 1 for the x cubed, and I've got -7, -5, and 10. The first number always drops down. And now I'm going to start checking my p over q's. So I start with 1, and then if that doesn't work, I'll try -1, and then I'll move on to 2, and then I'll try -2, and I'll keep trying these numbers until I have found all of the rational zeros. So you multiply 1 times 1 is 1, and then you add going down. 1 plus 1 is 2. Then I multiply 1 times 2 is 2. 2 minus 7 is -5. 1 times -5 is -5. -5 minus 5 is -10. And then 1 times -10 is -10. -10 plus 10 is 0. So I'm just doing multiplication and addition. I don't even need my calculator here. So I got 0. So what that tells me is that this is a 0. X equals 1 is a rational 0 of q of x because we got 0 in our final box. So what's nice about me doing this on my tablet is I can just erase my numbers. Otherwise, I'll try to do this multiplication and addition on my calculator in my head, so I don't have to write so much work. But then I just move on to the next number because we need to find all of them, and we know there's going to be at most 4. So I found one of them. I have 3 more to find. So now I'm going to try -1. And so I just make a new row. -1 times 1 is -1. -1 minus 7, -8. -1 times -8 is 8. 8 minus 5 is 3. -1 times 3 is -3. -3 plus 10 is 7. So I can see that this one is not a 0. Oh, I skipped a whole number. How did Let's try that again. I thought that was weird. I had this weird gap. I somehow skipped a whole column. -1 plus 1, that's 0. -1 times 0 is 0. 0 minus 7 is -7. It's a lot easier when you have graph paper. If you have graph paper, then you can keep this organized and not get lost. -7 times -7 is 7. 7 minus 5 is 2. That's -2. It's still not a 0, but at least I didn't skip numbers this time. So that didn't work, so I'm just going to move on. Now let's try +2. So 2 times 1 is 2. 2 plus 1 is 3. 2 times 3 is 6. 6 minus 7 is -1. 2 times -1 is -2. -2 minus 5, -7. 2 times -7 is -14. Add 10, -4, so that is not a 0. So then I try -2. And this is basically what like a calculator or a computer does when it tries to find the zeros. It's going through this process, trying to find them based off of our theorems to kind of help us narrow down the choices. So -2 times 1, that's -2. -2 plus 1 is -1. -2 times -1 is 2. 2 minus 7, -5. -2 times -5 is 10. 10 minus 5 is 5. -2 times 5 is -10 plus 10 is 0. So we found our second 0 here at -2. So we've got 2 of them. We know there's 4 of them maximum, so we want to keep trying. So next, I'm going to try 5. So I'm going to just kind of erase all I've got up here. 5 times 1 is 5. 5 plus 1 is 6. 5 times 6 is 30. 30 minus 7 is 23. I can tell already I'm getting into some pretty big numbers here because I'm now going to multiply that by 5. That's not, these numbers are just going to keep getting bigger and farther away from 0. So I'm just going to stop because I can tell already that's not going to get me anywhere close to 0 at the end. So let's try -5. So that's -5 plus 1 is -4. -5 times -4 is -20. That gives us -27. And these are getting farther away as well. So now I have 2 more numbers to check, 10 and -10. And normally I would keep going, but I've kind of run out of room on my screen here. So I'm going to just erase these and do 10 and -10. So 10 times 1 is 10. 10 plus 1 is 11. 10 times 11 is 110. This is going to get really far away here. Because now we're going to do 10 times 103. That's going to get really hard to get back to 0. And then let's try -10. So that's -10 plus 1 is -9. That's going to give us a positive 90. Gives us an 83. And once again, this is going to get really far away from 0. So we have found 2 irrational zeros, which tells us that the other 2 zeros, because we have 4 total, are either complex, so they're going to have imaginary numbers, or they're going to be irrational and have square roots. So we have 2 rational zeros. X equals 1 and x equals -2, because those are the 2 that came out to 0 when we went through this process. So it's a lot of kind of guessing and checking, but it's better than guessing randomly. You have at least a list of numbers to choose from. So I'm going to pull up Desmo so we can look at this one. If q of x equals x to the 4th plus x cubed minus 7x squared minus 5x plus 10. Okay, I'm going to zoom in a little bit here. So we've got 4 zeros. And so these 2 right here, so we've got this one with the decimal -2.236. That's going to be irrational. We did find -2, and we found 1. And this next one, 2.236, that's also irrational because it has, generally, if it doesn't come out evenly, like nicely with the decimal, it's going to be irrational. So we ended up with 2 rational zeros and then 2 irrational zeros. Basically the same number, a positive version and a negative version here. So all the math is supporting what we found. It's supported on the graph. This said to find all the rational zeros, and we found all of them. There are just 2 of them. The others are irrational. Are there any questions so far? Okay, so I've got one more. And this one says find all the zeros. So it doesn't want us to find just the rational zeros like we just did, but we want to find all of the zeros. So our degree here, the highest exponent, is 3. So our degree is 3. So we're going to have 3 total zeros that we need to find. So we will start with the rational zero theorem. So P is 6. So that's the numbers that divide into 6, 1, 2, 3, and 6. And then Q is 1 here. Only 1 goes into that. So our rational zeros, our possibilities, is P over Q. We're just going to have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So I tried to pick a problem here that had not a lot of possibilities. So I'm going to do what I did on the last example. I'm going to set up my synthetic division and then start checking these numbers to find the zeros. So I've got 1, -7, 14, and -6 for my coefficients. And then I'm going to just start by checking 1. So 1 times 1 is 1. 1 minus 7, -6. 1 times -6 is -6. 14, I believe that's 8. 1 times 8 is 8. 8 minus 6 is 2. Okay, so 1 is not a 0. So now I'm going to try -1. So let me just erase what I've got up there. That -1 times 1 is -1. Minus 7 is -8. Times -1 is 8. That gives me 22. And then times -1, that's a -22. That's getting further away. So now let me try 2. 1 times 2 is 2. 2 minus 7 is -5. 2 times -5 is -10. -10 plus 14 is 4. 2 times 4 is 8. 8 minus 6, I'm back at 2 again. So that's not a 0. So then we will try -2. -2 times 1 is -2. Minus 7 is -9. -2 times -9 is 18. 18 plus 14 is 32. This is getting further away. So far we haven't found any zeros. So now I'm moving on to 3. So that's the next choice here that we have. 1 times 3 is 3. 3 minus 7 is -4. 3 times -4 is -12. Plus 14 is 2. 3 times 2 is 6. 6 minus 6 is 0. Okay. So I have found a 0. I have found that x equals 3 is a 0. We can go on and we can also check -3, and we can also check 6, and we can also check -6. But if we're looking for all of the zeros, we're not just looking for possible zeros, but if it says we want to find all of the zeros, then I have a different method that I use. And actually, I think I need to add another slide to my presentation. So, whoops, that was not what I wanted to do. I just want to add a slide. Get back to it. I thought I was on the insert. There we go. Just blank. Okay. There we go. Okay. So I've got this blank slide. If I can find where my PowerPoint now went. No, it's giving me a note of. Let's just try this again. There we go. Okay, the part that I write on was disappearing. I have too many screens. I have 3 screens. I was getting lost. Okay, so now that I've got my, here's what I do. Once I have found a 0, that tells you that what your remainder. So basically this stuff that I had left over minus the 0 part, I can use to find the next 0. Our degrees start out as an x to the 3rd. When you find a 0, what's left over, you've basically removed something. So now you're at x squared. The next column would be the x, and then this is 2. So once I get down to a quadratic, then I just use the quadratic formula. Because when you're trying to find all of the zeros, at some point, you're going to have to use the quadratic formula because you're going to have zeros with square roots in them, or complex zeros. And if I kept going to use the rational zero theorem and there were no rational zeros, I would just waste my time because then I would have to use the quadratic formula anyway. So once you get down to something that's squared, then you're going to use the quadratic formula to find the rest of your zeros. So we're going to take x squared minus 4x plus 2 and set that equal to 0 and solve. So x squared minus 4x plus 2 equal to 0. And so when we use the quadratic formula, it's negative b plus or minus the square root of b squared minus 4ac all over 2a. So b is negative 4. So that's basically got 2 negatives there, negative, negative 4. Then I have my plus or minus, and then b squared, so that's negative 4 squared minus 4 times 1, which is a, and then c is 2. And then divided by 2 times a, which is 1. So I'm going to just start simplifying. So negative 4 is positive 4. Then negative 4 squared is going to give me 16. And then the 4 times 1 times 2 is 8, so that's minus 8 inside there. And then 2 in the denominator. And I move, when I do the quadratic formula, I move left to right, and then I go down and go left to right, just because it gets really long. So this is how I try to conserve space. So 16 minus 8 is 8, so I have 8 inside my square root, divided by 2. And we need to simplify that square root. So the square root of 8, we're going to simplify that radical. That is 4 times 2 inside there, and I can take the square root of 4 to get 2. So this is going to be 4 plus or minus 2 times the square root of 2 over 2. So now I'm going to split the fraction up. So that's 4 over 2 plus or minus 2 over 2 times the square root of 2. And you'll see that this reduces to 2 plus or minus the square root of 2. So those are our other two zeros. So our first zero we found with the rational zero theorem, and that was 3. That was what I tried here with the synthetic division. The quadratic formula just told us the other two zeros are irrational, not rational, because they have square roots in them. One of them is 2 plus the square root of 2, and one of them is 2 minus the square root of 2. So we have 3 zeros, but only one of them is rational. Only one of them was on our list of possibilities. But using that list of possibilities allowed us to find one and then get it down to a spot where we could use the quadratic formula. So I'm going to bring up my Desmos. Actually, let me, oops, bring up, come on. There we go. I want to graph D. The d of x is x cubed minus 7x squared plus 14x minus 6. So we've got 3 zeros here. So you can see the one that we found, 3, 0. And then these are our irrational zeros. So this is the 2 minus the square root of 2, which as a decimal would be 0.586. And then 2 plus the square root of 2 is 3.414 when you round it. So one of them comes out to a nice number, a rational number. The other two do not. And we had to find those with the quadratic formula in order to get all of the zeros. It says to find all of the zeros. And so these are our 3 zeros right here. Are there any questions? Okay, so that's the rational zero theorem in a nutshell. Obviously, technology does this for us, so you don't really have to memorize, really have to. I mean, you're learning in this class so that you understand what the technology is doing, and because it kind of helps you teach critical thinking. Let me try this number. Do I need to keep trying this number, or can I give up easily, early, because I know it's not going to get to where I want? It's kind of teaching you those thinking skills. So that's what you're getting out of this. You're not really ever going to have to do this by hand, because this is just what technology is doing in the background. So that's this. So we've got week 7 starting in 2 days. Our next live for week 7, I do actually have to move it an hour earlier, so it's going to be at noon Central instead of 1 on Saturday, just because I realized that I've got something at 3 o'clock and I wanted to make sure I had enough time after the live to process it, upload it, and then get to my other thing. So I've moved that to noon, but that will be listed in the announcement for week 6 or week 7 on Wednesday. That date will be there, but that's going to be at noon. And then the week 8 one, I don't think I have any conflicts. That should be at 1 o'clock just fine. So that's what we've got going on. If you guys have any other questions, you know how to reach me. And thank you guys for coming, attending, especially since I was out of town and couldn't, really send in a reminder or anything other than I've got the remind. But thank you guys so much for coming. So I will see you guys at the next one. Take care. Bye.